Uh, Thank you very much, and thank you all for coming. This talk is about NASA data and how we use it for societal benefit. How we use NASA data to solve day-to-day problems. In this particular case, health and air quality. And JT gave a very good introduction to NASA measurements. NASA has so many satellites orbiting. I think I did it. Yeah, okay. So NASA has so many satellites orbiting, and a lot of these satellites are making measurements of environmental factors, of the state of the climate, and we collect so much data in the distributed active archives, and this data can be used for societal benefits. As you can see here, these are the missions that have operated, are currently in operation. And if you look at what we have done, just within the last 10 years, there have been so many new missions, both looking at land, looking at the atmosphere, looking at the ocean, looking at water quality, looking at the air quality. And all these can be applied to environmental health and air quality issues. If you look at these missions, a lot of them are between not only NASA, but NASA and other agencies within the US. And a lot of them are also collaborative with other international partners. In particular, Landsat 8 is in collaboration with the US Geological Survey. SUMI NPP is in collaboration with NOAA. We have OSTM, JSON, which is in collaboration with the Japanese. Calypso is in collaboration with the French. So there's a lot of international collaboration in these measurements. And we have so many measurements that in the last, in between 2014 and 2015, we had 5 new launches of instruments. And this is the upcoming missions. If you look in the orange color, you see these new missions are missions that are currently in formulation, and these will be launched very soon. The missions in green are the ones that have been recently launched, and the missions in blue are missions that are in the extended phase. Extended phase means a mission has launched, it has achieved its 3-year mission, and it's going beyond that time. So missions like Calypso and missions on Aqua and Terra are more than 10 years. They were launched for a 3-year period. And so in the next few years, we are going to see several more instruments that are going to be based on the International Space Station. We have about 5 or 6 new instruments that will be on the International Space Station, which gives us a more cost-effective way of launching the satellites. And so just to underline the international collaboration, this is the OCO2 Orbital Carbon Observatory, the second instrument in that chain, in the International A-Train. The A-Train is a system of instruments that are following each other. The difference between all of these instruments is about 10 minutes. So they are looking at the same place on Earth. So you can get synergistic measurements, and you can get more products out of those measurements. And several countries have partnered with the US to achieve this. And so more and more measurements from space are going to be international collaborations between not only NASA, but NASA with several of the other space agencies. And getting to my talk today, before I do that, I want to say something that we really feel very lucky about. Between February of 2014 and January of 2015, we launched 5 instruments in space. This is a big, big achievement because we haven't done something like this in the last 10 years. So despite the difficult budget situation that most scientists are facing, this is a pretty remarkable achievement. And so with successful launch of SMAP on January 31st, we reached 5 new instruments. And those 5 instruments are The first one is SMAP. SMAP is a soil and moisture active passive sensor. It measures soil moisture freeze and thaw. These are important for hydrology, climate, the carbon cycle. This was launched on the 31st of 2015. As soon as right after it was launched, we launched GPM on the in 2014, and GPM is a replacement for the Tropical Rainforest Measuring Instrument, which measures global precipitation. It's the global precipitation measurement, and within a few months of that measurement, we were able to measure the tropical precipitation of Hurricane Isaiah as it was crossing the Hawaii Islands. And so that instrument replaced TRIM, which was a long-term measurement of tropical rainfall measurement. Another instrument in this group of 5 instruments is the Orbital Carbon Observatory 2, which was launched in July of 2014. Now, we think about carbon dioxide as a well-mixed gas present everywhere in about the same amounts. But if you look at the first measurements from OCO2, we see that carbon dioxide actually has a pretty significant variation all over the globe. There are areas where the carbon dioxide concentrations are much higher than others, and there are areas where it's much lower. As you can see, in the regions of the Amazon and the equatorial forests of Africa, there is pretty high amount of column CO2 compared to the Sahara Desert. And some of that is related to the biomass burning activities that happen in that region. And so there's quite a variation. We can only tell that there's a variation on carbon dioxide throughout the globe by looking at it from space. Measuring it from one point just tells us what the concentrations at that point are. Another instrument that was launched in this group is were launched on the space station, and that was the RapidSCAT, which measures the surface wind, some of which were shown by Jason. Now, how does an orbiting satellite work? We all tend to think that the satellite is launched and it revolves around the globe. But the satellite, most of the satellites that we launch are launched into a fixed orbit. This is a north-south orbit over the poles, and the Earth spins below the orbit on its own axis. And this enables us to pretty much view the whole Earth every day. So every day, the Earth spins around its axis one time while the satellite is orbiting above it, so you get a mapping of the whole Earth in one day. So I now start talking about air quality and health. These are really the topics that I wanted to talk about. The first part of my talk was introductions to satellite measurements. This picture is July of 2004. This was a period when several states in the US saw very poor air quality conditions. And this went from all the way from Ontario in Canada through the Midwest. As you can see, the smoke distribution that goes all the way down to the Gulf of Mexico that covers most of the Midwest. And a result of fires, in Alaskan fires, and these Alaskan fires were advected, and they affected that whole region, and the air quality in all those states was poor, actually exceeded the standards. There was no way we could have known about this without satellite measurements. The satellite could see a snapshot of this transport across that whole region. And when we looked at that, and when we looked at those measurements and we looked at the air quality increases, we saw that they followed exactly the path that was shown by the satellite. And so at NASA, we have looked at ways of demonstrating very innovative uses of the Earth observations for health and air quality and applying this in organizations' policies and business management decisions. And so we work with academia, we work with private organizations, we work with non-governmental organizations, and anyone who is looking to apply the data to produce a solution that is of benefit to society. And for every application that we fund, we look at groups that will prove out, develop, and will transition these applications and ideas to a sustained use of Earth observations in decision making. So if somebody has an idea where they can take Earth observations and develop them into a sustained use for decision making, then the Applied Sciences program is likely to fund such a project. A question was asked earlier. The data is there. We know the data is free and it's available to everybody anywhere from NASA. But most times the data is difficult to understand and to apply. So NASA has a capacity building organization that tries to train people in different organizations within the US and also in other countries on how to use the data and how to access the data and how to use the data. And so we have a project called SEVERE that has several hubs. One of them is in East Africa, another one is in South Africa, another one is in West Africa, and there's a hub in South America, and there are 2 hubs in Asia. And so they are developing these hubs where NASA people go and train the people in those countries on how to use NASA data and how to access NASA data. And I'll talk about that, and if you want more information, I can give it to you. We also engage, the Applied Sciences program tries to engage the NASA mission development teams at a very early stage and talk to them about what measurements are useful for society, what measurements do air quality managers need, what measurements do health practitioners need or people who are in public health. And so those measurements become a priority of these missions, and so they will take these measurements into account so that they are not developing missions that only produces science, but they are developing missions that produces data that's of benefit that could be used in decisions, in day-to-day decisions. So in these 3 areas form the Applied Sciences program. And you can look at any of their, if you go to nasa.appliedsciences.gov, you can look at any of their annual reports. It tells you what they do. And NASA Applied Sciences started as a result of the fact that NASA is very good at doing the things on this side. We're very good at technology, mission observations, data and archiving, research and analysis, models and predictions. We do these things very well. But to move from that side to the green side, where you have to make management decisions, policy decisions, forecasting, response and recovery, which society needs, we haven't done that in the past very well. Now with the Applied Sciences program, we have this bridge program that will fund activities that move our data and our knowledge from this side to that side. And we have had several successes in doing this. This has been only going on for the last maybe 10 years, and more intensely maybe the last 5 years, where we're starting to move our data and our science and our knowledge from just pure science to management decisions and applications for policy. And this goes for applications not only in the US, but all over the world for people who use NASA data. And this is part of the program that I work with. I have worked with the science part for many years, but now I do some work for headquarters in moving our knowledge to the other side. And currently, this Applied Sciences program has 4 main areas: health and air quality that I'm talking about today, water resources, disasters and ecological forecasting. And we had all the 9 areas, but we saw that for budget reasons we could not we could not do all of them, so we only do the first 4. But if there's any issue in any of the other 5, then we can pick it up. For example, if there is a weather-related emergency, like the Hurricane Irene that JT was showing earlier, then we can pick it up for that period of time. But we don't have a sustained program that addresses the other parts. Okay, so severe. Severe is it's a Spanish word for servers for data. I can't say the word, but it's an acronym that stands for these regional platforms for science data that have hubs in different regions. As I said, we have hubs in the Americas, in Africa, and in Asia. And on these hubs, they use Earth observations and predictive models for those regions, for their environmental management, for their disaster response and climate change adaptation. And it also includes a pretty intense program of training and capacity building, because whenever we go to a region, usually that region are interested in the data, but they don't have the training to use the data and also to understand the data. So we hold these workshops to train people, and then we actually do forecasts and we supply the managers. We do a lot of fires in different regions. So we take models, we have online maps, visualizations, decision support and training at the severe sites. And by the way, the sites are shown on the map on that side. Those are the current 5 sites that we have. They're developing a site in South Africa and another one in West Africa. And so if you have good ideas about using NASA data, we can talk about connecting you to this program. And I must say that USAID is also part of SEVERE. So why health and air quality? We know that climate change has a pretty positive impact on health and air quality. We know that it changes regional weather, climate change, higher temperatures lead to heat waves, extreme weather, changes in precipitation, as we have talked about. And this leads to different air pollution levels. And naturally, it leads to different contamination pathways for diseases, and also the transmission dynamics. The vectors are affected by temperature, precipitation, and this leads to health effects such as heat-related illnesses and deaths, extreme weather events that have a direct impact on health, air pollution-related health effects, water and food-borne diseases, and most importantly, vector-borne diseases that are very sensitive to environmental conditions. So we do a lot of research in this area, collecting data about these changes, but we're also starting to work with the health communities to look at not only adaptation measures, but also to look at mitigation measures for some of these diseases. And most importantly, to try to forecast before a disease takes root, or a vector-borne outbreak of a disease. Okay, you all know this more than I do. I'm more of an earth scientist, but the global emerging diseases are not only many, but as you can see, in the red is emerging diseases. In the blue are diseases that have been dormant and are re-emerging. And most of these diseases are either zoonotic or vector-borne. And because of that definition, they have a dependency on environmental factors. And if a disease has a dependency on environmental factors, then it means that you're likely to predict its outbreak if you know what the environment, what the environmental conditions are. And as you can see, we have several re-emerging diseases that have been dormant but are re-emerging, and a lot of these have dependencies on environmental factors like temperature, precipitation, soil moisture, most of the factors that NASA measures regularly. And then there are other environmental threats that are man-made. This is a case where there was an oil spill in the Gulf. This was in 2010. A lot of you have heard of this oil spill. It's a pretty massive oil spill that went on for a long time. The emissions from this produced a lot of crude volatile organic compounds that reacted with nitrogen dioxide to produce ozone. The air quality in that whole Gulf region was very bad for a long time. NASA satellites tracked the oil spill very closely, and we also had some airborne campaigns to measure the ozone, and we could tell how much of the ozone elevation in those regions came from this crude oil spill. And so this is some of the ways that we have set up systems that will react to some of these changes quickly. And so our objectives, if we go back to our objectives in the Health and Air Quality Program, are actually to support the use of these observations in air quality management and public health, in particular regarding infectious diseases and environmental health issues. Also, the implementation of air quality standards. The US has this national ambient air quality standards, below which each city cannot go or they will face fines. And so we have data that informs the state of the air quality that will inform policy and regulations both for economic and human welfare. The area also addresses toxic and pathogenic exposure and health-related hazards and their effects for risk and characterization and mitigation. This is when we look at what are the concentration levels of different types of pollutants like nitrogen dioxide or sulfur dioxide from satellites. And because we can look at the whole world, we can also look at intercontinental transport of some of these pollutants from one region to the other. And so we can look at the increasing development in some parts of the world and how that is affecting other areas. And finally, we look at what the effects of the projected climate change is on public health and air quality. And we support managers and policymakers in their planning on how to adapt and mitigate to these changes. And this morning, during JT's talk, there was a question about what is the ground truth. Even in the US, we don't have enough ground measurements that measure things like air quality, because the air quality standards are enforced from ground level measurements by the EPA. If you look at this map, the map of the US, the green regions are regions where we have monitors that can measure air quality, like what's the concentration of particles, NO2, SO2 in the atmosphere. The blue regions are regions where we don't have those monitors, but if we take satellite measurements, we can get measurements that are just as good as the monitors. So already, just even for the US that has a lot of ground-based monitors, we're using a lot of satellite measurements to augment the ground-based measurements. But even in the US, there are regions where we cannot use satellite measurements or ground-based measurements. The regions in white are regions where we don't have any measurements at all, neither from satellite nor from ground. And this is because in that southwestern region, the land is so dry, it's desert basically, and the reflection from the surface does not allow a good measurement from the MODIS instrument. And so in that region, we basically do not have measurements over pretty large regions. Of course, like in Phoenix area would have ground-based measurements, but that's for a very small part. But generally, for the most part, we don't have measurements. The rest of the world is even worse off. So in this case, if there was a smoke, as there was a smoke in Missouri in 2013, the air quality was really poor in some parts of northern Missouri. And because there are no measurements, if you used only the ground satellites, you would see that the air quality is pretty good. So you wouldn't have any reason to issue any kind of warning because the air quality is good. The green section on the top right-hand side there showing that the air quality is pretty good for that region, for the northern part of Missouri, and that's because you really don't have measurements there to tell you. If you include the satellite measurements, then you will see the effect of the smoke, and you see that that same region is now getting into the yellow region, which is a region for a moderately high air quality index, which requires warning to certain populations like the elderly or the young not to go outside for prolonged periods of time or not to engage in strenuous activity outdoors. So if you don't have the satellite measurements, you cannot make that decision. So this is the case where the satellite measurements are informing public health decisions directly. And so this event extended into Minnesota, and one of the Minnesota Pollution Control Agency staffers gave us this anecdote and said, this is the best tool I've seen so far that integrates satellite data with information from ground monitors to provide you this, this enhanced smoke condition that requires a warning. Okay, we also support the state air quality agencies. State air quality agencies in the United States are required to maintain certain air quality standards within their state. And if there's a violation, then they're required to submit what are called state implementation plans. These state implementation plans depend on models. The models depend on data. And we have scientists who work with this state implementation managers to provide data, especially for the distribution of clouds. In this case, this model, this particular scientist at the University of Alabama provides both the timing and the spatial distribution of clouds into the air quality model, and this improves the accuracy of this state implementation plan. And as a result, as you can see in the graph in the lower right, in the middle right corner, there's quite an improvement when you include satellite data as when you do not include satellite data in these models. And that gives you a more accurate state implementation plan, which leads to a better outcome. Okay. We also use satellite data in monitoring and predicting harmful algal blooms. These are blooms that happen in the waters, either lake waters or ocean waters, where there's a lot of harmful algae, and that can affect the water quality. In this case, a city in the U.S., the city of Toledo, is in Lake Erie. They draw most of the city water from this lake. There was a case in August of 2014 where the satellites found pretty high concentration of algal blooms just a few kilometers away from the water intake system that's shown on the upper right there. And so they focused that the bloom would make it to the water intake in time for the city to issue warnings to the people not to use that water for anything. So without this, the city would not have known that the algal bloom would have made it. And this is based on the ocean currents and the wind patterns and most of the parameters that are measured from satellite. And this is another case where a scientist is working with the city to come up with a solution of societal benefit. This is another case where the project's goal was to test the feasibility of utilizing satellite measurements to look at the sea surface temperatures the salinity of the water, and the solar radiation in combination with data from field sampling, bacterial data from field sampling, to determine whether there was a possibility of an outbreak of norovirus. Norovirus is a virus that affects the oysters, and the oysters are consumed either raw or cooked. But in either case, norovirus can cause some abdominal discomfort and also could lead to death in some populations. And so this scientist from Louisiana State University was funded by NASA. He divided the Louisiana coast into 30 regions, 30 growing regions, and looked at several parameters and was able to produce forecasts that were up to 90% accurate on the norovirus outbreaks based on satellite measurements of environmental factors. And so this was very impressive. It made the papers in that region, and the farmers, the oyster growers were very pleased with it because they could be sure that they only harvested oysters that were not infected with this norovirus, and that was beneficial to their economic activity. This is another scientist at Goddard. This model, it tracks Rift Valley fever and Ebola based on NASA's MODIS, TRIM, and Lancet. MODIS measures things like land surface, things like vegetation indices. TRIM measures precipitation, and Lancet measures surface conditions in sub-Saharan Africa to predict this Rift Valley fever. And they went back historically to see that sharply drier tropical forest conditions and lower NDVI values typically precede things like Ebola outbreaks by 1 to 3 months. And they updated the model specifically for West Africa using new data sets, and they worked with close partnership with the World Health Organization to provide some of these predictions. CV Africa took over this model in 2015 and use it regularly for these predictions. Again, this is another case where we look at vector-borne mosquitoes, Egyptian Aedes in Mexico, and then we look at land cover, vegetation, and surface temperature, going back several years to come up with a prediction for the outbreak of diseases that are borne by this vector-borne vector Egyptis Aedes. And this is the primary interest in this case was the outbreak of dengue fever in Mexico. And so when Bill Crossan went back several years, he could come up with some sort of algorithm that could predict the outbreak of dengue fever based on environmental factors. Okay, so as I said, we always train. There's a sampling training sessions by NASA through different universities where we have archived these trainings for different regions. And if you want the links to this, you can talk to me after the presentation. This is another case for malaria and meningitis. This is in Africa. And this is by a group from Columbia University. Again, they have developed a repository of data relevant for decision-making in malaria and meningitis control that is used quite frequently. There is an anecdote from the spokesman for the Ministry of Health in Eritrea that thanked the project for its results and stated that these map rooms are always useful for malaria predictions. And so they look at environmental factors and try to predict the outbreaks of malaria based on rainfall estimates, percentages, land surface temperatures, and such environmental factors that can be measured readily by satellite. And In here, this is like a good story that what satellites can show over time. We see the air quality in different cities in the United States, and the air quality here is measured by NO2. NO2 is nitrogen dioxide. Nitrogen dioxide is a toxic gas. It has effects if you breathe it. It leads to the production of ozone. And also, nitrogen dioxide, when entrained in clouds, leads to acid rain, leads to nitric acid and acid rain. And so this shows that between 2005 and 2011, several cities have shown quite a bit of improvement. The first one is Los Angeles. You see the big blob of NO2, elevated NO2, the region in red. And between 2009 and 2011, that region has decreased quite a bit. The number of counties covered by that region is a bit smaller. If we see Chicago, also if you look at the 2 years between 2005 and 2009, compared with 2009, 2011, this is just a 5-year period. Again, that blob has reduced quite a bit. Of course, the reasons for these are improvements in technology, regulations that have forced industries to control their pollution better. You see in the Northeast Corridor, which was very polluted in 2005, 2007, is much, much cleaner in 2009, 2011. So there's quite a bit of improvement. There's quite a bit of improvement in just those 5 years. And so these regulations and the development of technology that reduces pollution is doing something very positive. If you look at Denver, it's very dramatic. The red is almost gone completely if you look at 2005 to 7 and 2009 to 11. So those 2 years are pretty clean for the Denver region. The map in the US is showing you what it was in 2005 and then what it is in 2011. And you see that there is quite an improvement in NO2 concentrations. Regions like Atlanta have improved also. And even the San Francisco Bay, the red is completely gone. You can see that it's much, much cleaner, as is Houston, as is Tampa. So most of the major urban areas have improved in air quality because of improvements in technology and also improvements, regulations that have required reductions in these pollutants. Okay, so I go back to the theme. The theme was take the data you measure, and the objective for measuring this data is scientific in the beginning, and see how you can apply it to air quality or health or public health management needs. In this case, pollution monitoring, exposure assessment, air quality forecasting, source attribution and events, quantifying emissions, assessment of natural and international influences, understanding of transport chemistry, aerosol processes, understanding of climate and air quality. And this is just for this limited area of the health and air quality applied sciences team. And so we take satellite measurements, which is our main function to measure from satellites. Then we use suborbital platforms. These include things on the surface and aircraft, balloon-borne measurements that are not on satellite. And then we also depend on modeling quite a bit. So a lot of the measurements go into models to help us predict the future. And so we set up teams that can look at this that can respond to environmental disasters very rapidly, and we fund them to do that. Okay, so this is a case where a state had a very elevated ozone concentration. And there was no reason at all where the ozone concentration should be elevated in that state. And in the US, the Environmental Protection Agency requires ozone concentrations to be below a certain level. And if a state doesn't have their ozone concentrations below a certain level, they are considered a non-attainment, and eventually they are considered in violation, and eventually there can be enforcement. Enforcement can be withholding funds for highways or any other way that the federal government can enforce the non-compliance of its regulations. In this case, in Wyoming, there was no reason why ozone should be elevated. So it either had to come from outside or it had to come from somewhere else. And there was no way that the state of Wyoming could prove that this ozone came from somewhere else, so they would be in violation. Luckily, there was a NASA experiment in Southern California at that time called the Alpha Jet atmospheric experiment that did some measurements of ozone. There was a model that ingests a lot of NASA satellite data. So we looked at the satellite data above Wyoming at that time, plus the ground-based measurements, and then they could show that the ozone that was observed in that state came from the stratosphere. It came from very high up above. There were conditions that made it possible for the ozone to be advected down to the surface, and this event was documented and was presented to the EPA, and this is called an exceptional event demonstration. If you can demonstrate that you didn't do it, that it came from somewhere else, then you don't suffer the penalty. And so the state was very happy when we could provide the data that they could use to demonstrate this exceptional event so they could escape the penalties. The EPA accepted for the first time in the summer of 2014. To give you a background, the EPA has never accepted satellite data without strong proof from ground-based measurements. EPA depends on ground-based measurements almost totally. This was one of the very first cases where, working with the Applied Sciences Program at NASA, the state of Wyoming, and the University of Wisconsin, that we could demonstrate to them that this was an intrusion that came from the stratosphere, and so the state did not get penalized. And this was accepted, and for us it was a major achievement because EPA is very skeptical of, and as a lot of people are, of satellite data. People want ground truth. So this was a good story in that year. Okay, we're also monitoring things like how is the air quality changing because of certain activities. As you all know, Alberta, Canada embarked on a lot of oil production from the oil sands. From 2005, there's been increasing oil sand recovery, and this is shown by the NO2 columns that are measured from space. This area used to be pretty clean before that, but it's beginning to develop quite a bit of NO2 elevated concentration, and that's because of the tar sands. And when we plot a trend, we see that that trend is increasing from that time. We know that oil sand extraction requires a lot of energy. Combustion produces a lot of NO2, so this is NO2 that is not coming directly from the oil sand, but it's coming from the activities that go into producing the oil sands. So observations show that this is increasing at 10% per year, and that's pretty significant. And very soon, that will begin affecting the northeastern parts of the northwestern parts of the U.S., which have been pretty clean from ozone. Of course, there are activities of fracking that are going on also in the northwest. So between those two, the air quality in that region is likely to change over the coming years. And so we can monitor such activities by satellite more than we could by ground measurements. Okay, again, this is the same thing showing the improvements in air quality between those two. And as I said, this improvements are due to technology, emission control devices, and more fuel-efficient cars over the last few years. And so NASA's air quality science team continues to produce such proofs that the regulations are doing something positive, so that we can get more regulations. Okay. The good thing about satellites also is that we can look at everywhere. So we can look at places like India. In India, there are 361 ground-based monitoring stations, and only about 70 of these are near power plants and industrial regions. So while they do their best to make these measurements, it's a large country. You can't put ground-based measurements everywhere. And as we have discussed this morning, the ground-based measurements are expensive to run and maintain. So we have worked with scientists in India to look at what the distribution of, say, SO2 emissions are. And we see that SO2 emissions have been increasing, if you look at 2005 and 2012, by more than 60% over that time, which is a very dramatic increase in SO2. SO2 not only has health effects, but also leads to acid rain. When it's embedded in clouds, it leads to the formation of sulfuric acid. And so when you get acid rain has many impacts on agriculture, on buildings, on welfare. So it's not a good thing to have. So this has been increasing quite a bit. And recently, in 2010, India has become the second largest, after China, emitter of SO2. That position used to belong to the United States. The United States was number 2 after China. But now from 2010, India, because of a lot of these power plants, and a lot of the sulfur dioxide is coming from coal-fired power plants, and some of the high sulfur coal produces a lot of SO2. And as countries develop, there is more need for energy, and a lot of the energy comes from coal. And we see that these dramatic increases are possible at that rate. And this can only be seen using satellites. You cannot use ground-based measurements to make these kinds of measurements. Again, we have done some trainings in India itself. We have a Sevi hub there. Every training we do, we have webinars that we do over the web. We also have trainings that we send people to those places to provide the end users with technical professional workshops, and also to build long-term partnerships with these communities and institutions. And more, the focus has recently been on developing countries, to provide training in those countries on how to use this data to monitor environmental conditions in their countries. We provide online courses to policymakers, environmental managers, also modelers and professionals, universities, people who use the data for academic reasons. We also provide them. We provide this throughout the year. We have a website. You should check. If you go to NASA appliedsciences.gov, appliedsciences.nasa.gov, it will lead you to this training satellites, this training links, and you can find out when the trainings are going to take place. And you can also request trainings for your region if your region is an upcoming user of NASA data. And that's most easily done through one of the severe hubs. Okay, so in 2014, 2015, this was our golden year. We had this campaign called Your Planet is Changing, We Are On It. And this is when these satellites were launched in a period of 5 years. I'm not seeing one of them here. But the 5 new Earth science missions in just over a year, this is an opportunity NASA has not had in over a decade. So the outlook is very good. Even under the budget conditions, we have been able to launch satellites that are really useful for society. The global precipitation measurement is like you're having a rain gauge in every village. You're having a rain gauge in every village because it's measuring precipitation everywhere around the world. Not only rainfall, but also snow precipitation. OCO2 is an important measurement. It measures how much carbon dioxide is around the world. Rapid SCAT measures surface wind speeds, and CATS measures things like the aerosols in the atmosphere. Aerosols are these very small particles that have an effect on air quality. And so it's on the International Space Station. It makes these measurements both day and night. And of course, SMAP, the soil moisture active passive sensor, measures the moisture in the soil, which is very important for agriculture, for climate, for water cycle, energy cycle. These are all very important measurements for society that NASA launched in those years. So this is something we were all really proud of, and we had a campaign that is still under this website, nasa.gov/Earth right now, that talks about these 5 launches. And I think I'm getting to the end of my talk. That's my information. We want to do these measurements collaboratively with everybody. Ground truth measurements are always important for satellite measurements. So we work with colleagues, collaborators all over the world to not only to get ground truth measurements, but to get measurements that we can use for our models. So thank you very much for your time, and I think I'll take a few questions.
Thank you, Dr. Omar. First questions I'll take right here, and then we'll get a couple more, and then we'll leave you for the rest of the day.
Thank you very much, Doctor. This is Judy Saw from Mother Channel TV and Cape Town TV. And my question to you is, we've discovered that all the plastics and all the chemicals, 80% of everything made on the land, ends up going through the aquifers and ends up in the sea. The same sort of particulates are part of the sulfur dioxide and nitrogen oxide. What happens to all of those? Do they just become dissolved in the rain and then end up in the sea as well? Are all of these things that we produce by burning all these coals and various other substances that are particulating into the earth with the smoke, are they all ending up in the sea as well? Are they all part of the problem, or do they dissolve into something else or become something else?
Yeah, I can't speak much for the plastics, but I'm sure those end up on land. The NO2, the SO2, the particulates that come from pollution, all this stuff ends up back on the surface, whether it's the land surface or the sea surface. There's no preference which one, but they do end up back on the surface. We are more concerned about some of the secondary effects, like of NO2 in producing ozone. That is a gas that is harmful at the surface. I mean, ozone is good at high elevations, but ozone at the surface is harmful to health, respiratory diseases, and things like that. So a lot of these gases somehow end up on the surface. In some cases, it's good. You need some nitrification, so NO2 in the soil is not necessarily a bad thing, but I would defer to experts to say whether NO2, SO2 getting entrained back into the soil is a good thing or bad thing. But I know everything ends up on the surface. nothing leaves our Earth to outer space that we produce here.
Any more questions? Right here.
Yes. I live just a few blocks from the Gulf of Mexico, and you mentioned two events that I assume would have personally affected me. Definitely the Gulf oil spill, because I could walk there and see it, and I could smell the difference in the air from my home. And then you mentioned about Alaska, the fire,
Right.
and that it was always... I wanted to know, how closely do you work with state agencies? Do they have access to this information? Because this is actually my first time hearing of it.
Right. So as far as states and local organizations, and I mean public policy managers, whether they're in the US or in other countries, we seek out anyone who uses NASA data in their policy decisions. We also talk to states, policymakers in different places about NASA data and how they can use it. We look at what they use it, what they do, and we say, we have this data, this may help you understand this better. So we try to be proactive in that, but most of the time, we work with universities and academia and say, give us ideas on how NASA data can be used to solve societal problems, and we'll fund you for 3 years to build a partnership, develop a tool or a process that this data can be applied in a sustained way, and after 3 years, transition that tool or that process to the state or to the policymaker. And I want to reiterate that this is not only in the US, but we do this in all countries. The only requirement we have is the person in another country has to have a partner in the US who is receiving funding from us to develop this tool, maybe to be applied in Uganda or in Peru somewhere. And so we do a lot of that. We have a lot of NASA scientists at universities who work with outside agencies, NASA scientists at universities who work with state policy implementers.
One more question.
Yeah, hi, Belinda Perryman from a UK local authority. I think all this data is fantastic, but somehow I got the idea it was a bit out of date. I mean, like the lady there was saying, because you showed the 2010 data, so what did NASA see? What happened? What was the awful? What was the healing? You know, what did you see? And the same way, all that beautiful city data only went to 2011. Does that mean the next 5 years isn't available yet? And so I'd love to know sort of a real up-to-date thing. You know, what's happening in Mosul? Are you able to see what's happening with the burning oil fields? Are you tracking it? Something a bit more sort of up-to-date and live on it?
Yes, that's a very good question. Yes, we are. And for the NO2 data, we're producing the latest complement. These hyperwall images are being updated constantly. I'm sure we'll have the latest ones very soon. It's a question of when the scientists produce the data, when they get it to us. For NO2, I can tell you it's improved beyond that for this time. There is no reason to believe that it's going to get any worse. For some of the anecdotal cases I've shown, these are just cases for illustrative purposes. For example, the fires that were burning in Alaska, this happened in 2004. It's quite some time back. But it shows that we can do this today. Whenever there is an elevated air quality situation, this was the most dramatic that we could show. So whenever there are people who are looking at the Mosul fires, the crisis in Syria, there are people who are looking at data from all those crises. And so it's just how representative, how dramatic it is. There is no time to show everything in the applied sciences in this time. But those two cases you have mentioned, particularly, I have seen data from that region, from Syria and from the oil fires in Mosul. And there is some data also from the Kuwaiti fires back in the 90s, yeah.
All right, thank you, Doctor. Can we have a round of applause for Dr. Ali Omar and a wonderful talk?